Test, test, test. Okay, for people online, can you hear me? All right, thank you. Okay, good evening. Let's get started. We should be able to finish the Lagrange multiplier and then get on with the new topic. It's called double integral. So let's have a very quick review on the constraint problem. So if you recall, the general format of constraint problem is you have an objective, and the objective is to, for example, to minimize a function. And we sometimes call this as a cost function. However, we also have a constraint. So the constraint is g of x, y equal to c. Now that's the overall picture of the constraint problem. So let's take a look at this problem using function two variables. Okay. And I illustrated this in the previous lecture. So your cost function is basically the surface z equal to f of x, y. Your constraint is basically a curve in 3D in the xy plane. And now what happens is it's like you have a person A at here, and the person A will go along the constraint curve g of x, y equal to c. At the same time, you also have a person B right on top of a person A, which is also on the surface, okay, z. As person A is going along this constraint curve, and person B will trace out curve on the surface, which is a cost function. So the point here essentially is to find the minimum location, okay, based on the traced out curve by the person B. So that's the objective. So now let's take a look at how to formally solve this kind of question. Okay. So I'm going to lay down a number of conclusions, or a number of results, and whatever I have laid down in here, okay, they're not going to be anything new. We have all learned of this, okay? But it's a collection of information, okay, based on what we have learned. Number one, this constraint. Okay. This constraint g of x, y equal to c. Okay. Now, this is a curve. Okay. It's a curve at the same time, right? And it is also a level curve for example, a w equal to g of x, y. Right? So it's try to establish this connection right here. I mean, even though this is just a curve plotted in xy plane, now if you think in a bigger picture, where is this curve from? This curve actually probably comes from a function in two variable, which is surface. And if you slice the surface with w equal to c, then you get this level curve, right? So even though this is a curve in the x plane, it's actually a part of a level curve of this surface at here. Okay. So that's number one. So we didn't do anything, we're just saying here, right? Number two, now the moment you establish that this is a level curve, okay, or just a curve, then you can calculate the gradient. Okay, you can calculate the gradient del G. So for example, you calculate the gradient, okay, at this location. Then del G, so I'm just arbitrarily drawing here, del G may be pointing this way. Okay. So another thing, a fact is, remember, right? The fact is the person A is going along the curve, the constraint and here. So as person A is going in that direction, so we can always use U hat to indicate the direction of moving. And U hat is the tangent vector, unit tangent vector to that curve or to the constraint curve G of xy equal to C. Okay. So U hat is a unit tangent vector to G of xy equal to C. Okay. So now here's a fact I want you to jog your mind. Remember when you calculate gradient, okay, when you calculate the gradient of function two variables, in one of our lecture, we actually proved that the gradient vector is perpendicular to what? To the level curve. Or the gradient vector is perpendicular to the unit tangent vector at that location, right? So never mind if the function z equal to fx, just if I just focus on this level curve, if I just focus on this function here, if I calculate the gradient del g, and del g is actually perpendicular, right, to the unit tangent vector at that location of the curve. Okay, so that's one of the findings when we learn the gradient vectors. Okay, so that's number one fact, right? So del g perpendicular to the u hat. Okay, let's keep going. Okay, so let's call this as a fact number one. Okay, this is fact number one in here. Number two, okay, so let's look at that directional derivative formula. So here's the directional derivative, okay, formula, which is df over ds equal to del f dot u hat, right? So what we're trying to do is, so for example, this is u hat, okay, so u hat right here. So here's a 1 point. So you said, okay, I'm moving in the u hat direction. Then, given the regular problem, you say, okay, so if you're moving in the u hat direction from this location, then the question here is, then what is the directional derivative for the function f when you're moving in the u hat direction by a certain amount of displacement, right? How do you calculate? You calculate using this one here, okay? So what this does, right, if you recall, this basically gives you the rate of change for the function f, okay, when there is a change in u hat direction. Okay. It's a slope concept, right? Yeah. It's a slope. And what's the slope? The slope for a certain location of a certain curve. Okay. So now the question basically is, if this is a slope concept, okay, then when the df over ds equal to 0, okay, when df equal to df over ds or equal to 0, then guess what? There's rate of change equal to 0 at that location, right? Meaning you are at a certain critical location, basically, right? So for example, if this is a curve right here, if I got a df equal to 0, df over ds equal to 0, okay? So the slope equal to 0, then you must be at a certain critical location, right? So that is a special situation, df over ds equal to 0. So we need to consider that. And if a ds over ds equal to 0, and if you look at the formula, that basically give you the gradient must be perpendicular to the U hat. Okay, so must be perpendicular to U hat. So now you can combine this one here. Let's call this as a fact number 2. Okay. All right, so what does that mean, right? For example, at this location, okay, at this location you got del G, at this location you got U hat. Okay. At this location, you may get, I'm just arbitrarily drawing, you may get the del F like this way here, okay? However, at the certain location where you reach this minimum point on the intersected curve, okay, at somewhere, then what happens is you're gonna have 2 different conditions satisfied. You're gonna have this condition satisfied. You are also gonna have this condition satisfied. So both of these conditions will need to be satisfied when you reach at certain critical location. So this happens, so these 2 conditions happens at critical locations. I'm going to show you an animation using Maple after the example here. Okay, we'll have a better understanding of that, what this means. All right, so basically, I'm going to focus on these 2 vectors here. Okay. So let's say this is your constraint curve, g of x, y equal to c. Okay. And then when the 2 condition happens, that's assuming it happens somewhere here. So U hat is right here. Del G, let's see this way here. So del G is perpendicular to U hat. And what about the del F? So with the del F also perpendicular, let's assume del F is pointing this way. It could be the other way, okay? So remember, all the vectors are in the same plane, right? The 3 vectors are in exactly the same plane. Okay. And now we know del F is perpendicular to U hat. Del G is perpendicular to U hat. Okay, so you can think about it. When you have 3 vectors, which are all in the same plane, 2 of the vectors are perpendicular to the 3rd vector, which is U hat at here. So what do you think this relationship between the del F and the del G? Yes. So you're thinking cross product between del G and U hat or del F and U hat? Okay, so that's one way to think it, but just look at, observe it. Yes, go ahead. They're parallel, exactly, right? So you can use maybe 3 panes to illustrate. When you get 2 vectors are perpendicular to the 3rd vector, and the other 2 vectors, they must be parallel to each other as long as they're in the same plane, right? So they must be parallel to each other. So these 2 conditions essentially translate to this conclusion, right? So can you see the logic flow here, right? We are looking for the critical location as the person A is moving along the constraint, right? We're looking for the critical location traced out by the person B. And we reached the conclusion there is that critical location only happens when the del F is perpendicular to the U hat, and also del G is perpendicular to U hat. And this condition translates to the 2 grading vectors has to be parallel to each other. So basically, this parallel condition, right, give us the critical condition, right, or the critical location. So this is where we're going to work on, right, for the next step. Right? So if I want to find the critical location, okay, because the B could trace out on the surface on the cost function, then I need to find where am I going to have, which location will give me the del F parallel to del G. Okay, so let's mathematically find that. First of all, you know, wording a parallel, it doesn't work very well when you derive a mathematical equation. So let's translate, right? Translate into a math equation. When two vectors are parallel to each other, mathematically, they are just a what difference? Scale difference. If they're only a scale difference, I'm just going to introduce a constant lambda here, right, to represent the scale difference, whatever the lambda is. Okay. Now, conventionally, you can do this, but in the traditional way for Lagrange, I would say the lambda here, basically Lagrange multiplier, we add a negative in front of it, okay, as more of a convention, yeah. Even though the negative really doesn't really matter because negative can always incorporate it into the constant, but people typically just put a negative over here, right? So I'm gonna just put a negative over here, so call it negative lambda. Okay. So the lambda here, right? This is called the so-called Lagrange multiplier. Okay, so this condition, right, is what we can make use of. Remember what this condition is all about. This condition will give us the critical location. Or in other words, when you have a critical location due to the constraint problem, at the critical location, you will have this relationship. Okay, so if I expand this equation here, I get partial f, partial x, partial f, partial y, equal to negative lambda partial g partial x partial g partial y. Okay. So because the two equations are equal to each other, so I have partial f partial x, right, equal to negative lambda partial g partial x partial f partial y equal to negative lambda partial g partial y. And further simplify this a little bit, just to move everything to one side. Okay. So that parallel condition is equivalent to the math writing given over here, the two equations. Okay. So now I have two equations over here. Right? So let's think about it. The objective is to find out, right, the minimum location. So location means where is the XY coordinate representing that location to give me the minimum location traced out by person B. So looking at these two equations here, obviously function f and g are function of x and y. If I take a partial derivative, I will have certain expressions of x and y here. So I have two variables, x and y, and plus the third variable, the lambda, or the Lagrange multiplier. Okay, so then I got two equations, three variables here, right? So if I want to solve, that's not enough. I need the third equation in order to solve. So what's the third equation? It's already in front of us. The third equation is the constraint. Right? So your x and y is constrained to g of xy here. So the third equation is this. So now you got three equations, three variables, And you'll be able to solve for x, y, and lambda. Technically, you can get lambda too. So let's call this is equation 1, 2, 3. So with these 3 equations, we'll be able to get the critical location, okay, traced out by the curve by the person B. Good. So we'll take a look at example how to solve this one. But before we take a look at example, I want to introduce a slight variation of this formulation in here. Okay. So, a little variation, and this variation is more common if you study further into optimization problem. So what we do is we define a new function. We call it L, X. L is a function of x, y, lambda, and it is defined as f of x, y plus lambda, then g of x, y minus c. So it's constructed using the given cost function f of x, y, and the constraint g of x, y, and plus the Lagrange multiplier lambda. And that's how this function is defined. And this function has a name for it. It's called the Lagrangian. It's called a Lagrangian function. All right. So you might wonder, so what does this new function do? How is that new function related to the 3 equations that we have just figured out, right? Okay. So now, if I ask the question here is this, I give you this function L, a function of 3 variables, and then I ask you, okay, can you find the critical locations, okay, given by this function? So what would you do? We did an unconstrained problem previously, right? Z equal to f of x, y. So what is the first step we did when we try to find the critical location of function 2 variables? We did what? What test is that? First derivative test. Or in other words, you letting the greetings of the function equal to 0, right? So you do exactly the same thing, even though this is a function of 3 variables. It really doesn't matter. The first degree test is always like that. So basically you set the greetings of this function equal to 0. And that's universal, right? When greetings is 0, meaning you have reached a critical location. By doing this, then what do we get? You know, we basically have partial L over partial X equal to 0. We have partial L, partial Y equal to 0, partial L, partial lambda equal to 0. That's the component. Those are the components of the greeting vectors. Okay, so then what does partial L, partial X give us? Here's your function L. And if I take a partial derivative with respect to X, okay, based on what we have on the right side, you have partial F, partial X, plus lambda is constant, and partial derivative inside with respect to X equal to 0. Then similarly, you get partial L over partial Y. And the last one, partial L with respect to lambda. So when it's partial lambda, everything else is considered as a constant. So you get g of x, y minus c equal to 0. Okay. So now it's clear, right? So the result of setting the gradient del L equal to 0 give me exactly the same result as we have derived momentarily. The same result. Okay. However, as you can clearly see, right, this part of the derivation here, okay, this part of derivation, you actually can call this is a unconstrained problem because I don't have any constraint, right? I only have a function given as L. So essentially the introduction of this new function in here, or the Lagrangian, the purpose is transform the original constraint problem into an unconstrained problem at here, right? So that's the idea of this Lagrangian, introduction Lagrangian at here. Now, when you solve this kind of question, okay, for Simons or okay, it doesn't matter which one you use, but I think most of the time you can just use this equation 1, 2, 3, and that'll be okay. Yeah. All right, so now let's take a look at example together. See how we can use the Lagrange multiplier approach to solve for a constraint problem. All right, so let's minimize this function and subject to g of xy equal to xy equal to 3. So let's do this one. I'm going to strictly follow these 3 equations in here. Okay. All right. So first equation is partial f, partial x, lambda, partial g, partial x. Okay. First equation. We have function f right here. We have function g, which is this xy. So then taking the 2 partial derivative, it wouldn't be too bad. The first one give a 2x, partial g or partial x give me y, so lambda y. Okay. So this equation needs to be 0 because this is our, and again, a new equation number 1 now. Second equation is this one here. So that give a 2y lambda x equal to 0. So that's equation number 2. The third equation is the constraint. So we get g of xy equal to c. So that gives me xy equal to 3. 3 equations, 3 variables. And now we need to solve for the x, y. The question asks for lambda, then you can solve for lambda. Okay. But sometimes you solve for lambda through the process, okay, at the same time. Again, these kind of situations often give you a set of nonlinear equations. Okay. The rule of thumb is substitution rule again. Okay. But sometimes substitution can be done in a different ways. So for example, what am I substituting? Should I derive x and substitute to the next one? Or should I substitute y and derive y and then substitute to the next one, right? That often in time, sometimes needs a little bit of trial and error, okay? Yeah. So there's no set in the stone type of approach. There's really some experience needed. So here's what I'm going to substitute from this equation 1. I'm going to solve for lambda. Now we get negative 2x over y. Then we'll substitute into the equation number 2. So that's 2y minus 2x over y times x equal to 0. A little bit of simplification, you get x squared equal to y squared. Okay. So x squared equal to y squared, you will have two results coming out of this x squared plus y squared. So you get either x equal to y or x equal to negative y, right? Yeah, so both of these conditions will satisfy x squared equal to y squared. So now I'm gonna have to look at it separately. So let's look at the condition results x equal to y. So if x equal to y, I'm going to substitute into the equation 3, okay, that constraint over there. So obviously you get y squared equal to 3. So then you have y equal to positive and negative root 3. Okay, so y has two solutions, then x must have two solutions too. So then when y is root 3, because x equal to y, we're dealing with x equal to y here, then x must be root 3. When y is negative root 3, your x is negative root 3. So you basically, you get two critical locations, right? So there are two locations, critical locations. Okay. All right, that's the results based on x equal to y. And then let's take a look at the next result when x equal to negative y. So we'll do the same thing and we'll substitute into equation 3. So what am I going to get? I get a negative y squared equal to 3. So what happened here? Negative y squared equal to 3. Is that possible? Is that possible? It's impossible, right? You know, because your y square is guaranteed to be a positive number. How could you put a negative sign in front of a positive number, give you another positive number, right? Yeah. So this is impossible. Basically means this condition, okay, we should discard it. It's not applied, doesn't apply in this question. So the only solution we're getting here is these two critical locations. Okay, yeah. Now, I didn't solve for lambda at here, but you can easily solve for lambda once you get x, y value, because you have your lambda equation right here, right? Lambda equal to negative 2x over y. So you can solve for lambda too. So lambda, you solve for lambda, which is negative 2x over y, sorry, 2x over y, right? Yeah. So you're going to end up with negative 2 for lambda. So that lambda value. Okay. So finally, we should see some questions. So then what is the minimum value, okay, given this constraint? Because you're trying to minimize, the question is trying to minimize this function subject to the constraint. So then what is the minimum value at the end? Right? So you can calculate the minimum value. So minimum value for f xy equal to x squared plus y squared, right, is what? Is to substitute the two values, okay, into the function, you get a 6. And when you substitute negative value, negative root 3, you're going to get 6 too. Good. All right. So what exactly actually going on here? I mean, this is very purely mathematical here. I want to show you a little bit of animation. So let's see, what is the current question? The current question here is this function, right? X squared plus y squared, and this constraint. So x squared, y squared, without we have dealt with so many times, this is a paraboloid, right? It's paraboloid. So what is the constraint? Constraint is g of x, y equal to x, y equal to 3. So this is high school. So when x, y equal to 3, this is x, y axis, okay? So you actually get, what do you get? You get a paraboloid, right? A parabola. Okay, if you look from the top, so you get a parabola, one in this quadrant and the other one is in this quadrant. Okay, yeah, that's the constraint, the red one, and this is your cost function. So if you got a person moving along the constraint right here, and then you get person B, okay, we'll trace out the curve. We'll trace out a curve and right on the top surface. And that location, right, is the minimum location due to the constraint. That makes sense? Yeah. So because of symmetrics, so if you go along the other side and you get on the other side of the surface, you get exactly actually the same minimum value like we show here, 6, right? Okay. So now I'm going to show you using computer animation here to show you a little bit more better visual. Okay. So this is the one. Let me see which one is it. Yeah. So both of them are good. So what you see in front of you here, you see the paraboloid x squared plus y squared, okay? And then the red curve here is the xy equal to 3. So I only plotted one. Okay, there's of course the other one mirrored on the other side. Then there's a red color vector, and then there's also a blue color vector, right? So can somebody actually tell me which vector, both of them are greeting vectors, okay? So which vector is the greeting vector for the surface, the paraboloid? Which vector is the greeting vector for the constraint g of xy or xy equal to 3? Yes. That's right, below the surface. How did you identify? You can literally actually probably see this is the blue one, and that circle is the level curve, right? So you can see the blue one is perpendicular to the level curve. You can also see the red one is perpendicular to this constraint xy equal to 3, which is also a level curve, right? We mentioned that basically. Okay, so that's something you can identify. Okay, so now I can move around, observe while moving around this constraint here. Okay, observe the relationship between the red and the blue, and also observe the dots. The dot is person B. Okay, this is person A. So if I move around here, okay, so let's starting from this right side here. Okay. Then as moving to the right, okay, you can see the person B, of course, the person B is always on surface. And person B will trace out a curve. Right now I didn't draw it. Okay. And look at the variation between the two greeting vectors, right? So right at here, they become parallel to each other. And that person B is literally at the minimum location along its path. Right? So that's the idea of how the Lagrange multiplier is defined. The del F is parallel to del G, and del F equal to negative lambda del G. Right? So this is the idea of this constraint problem here. I think the next one here, I probably trace out everything. So then you have a whole bunch of curves basically going on here, right? So that is the curve traced out by the person B on the surface. And this is the minimum location, obviously. So also, I want you to observe another thing here, which is probably very obvious from this drawing. So look at what happened between the constraint curve and the level curve corresponding to the location of the person B. So the blue one here is a level curve. Depending on where the person B is on the surface, you can always slice it to get a level curve, right? And we know this is a paraboloid, so wherever you slice it, you get a circle as a level curve. So as you can clearly see, right, that level curve, the blue one, okay, of course it changes, okay? And when the person B reach this minimum location, the level curve from person B and the constraint, they become tangent to each other. So this blue curve and constraint, they become tangent to each other. So that's another fact, okay, for the constraint type of problem. Okay, when you reach at a critical location, due to the constraint problem, the two level curves, okay, one is from the surface, the cost function, the other is the constraint, they're tangent to each other. Okay, so if you just sort of think back a little bit about the approach at here, right? I think the idea is not that bad because you just had to create the three equations. And of course, which involve calculating the greeting vectors. Okay. And to solve for the three equations using substitution rules. Sometimes just bearing in mind that you might not be able to solve in the first run. Sometimes you have to go back and then maybe substitute it differently, but that's fine. Okay, yeah. Okay. So that's pretty much about it, about this constraint problem. Okay, so you have an unconstrained and you have a constraint problem. There's much more to the optimization area, to the subject, but this is very much the start, the beginning. Okay. Any questions? Okay. All good? All right. So now we're going to introduce a new topic now. Okay. Again, it's all about multivariable functions. Okay. So we're going to look at integrals of multivariable functions. Now, the first thing we're going to look at is double integral. Okay. When you have a function 2 variables, it's about double integral. When you have function 3 variables, then it's going to be about triple integral. Okay. That's where we're going to learn. So let's start from a very beginning. Okay, let's understand basically what double integral is all about. Let's start from function single variables. So when you deal with a function of single variables, one of the things that you have learned a lot is that when you integrate from A to B for this function, you're going to get the total area. Okay, so how that interpretation is derived? So here's how you do it. Let's say this is A to B, and then you pick a point somewhere in the middle. Let's call this is XK location. And then you take a very, very small segment, okay? Let's call this a delta XK around this location. And now you can create basically a rectangular area, okay, based on the delta XK. So you can create a very small rectangular area. And then the area of the little strip, right, equal to the base length, which is delta XK, multiplied by the height. So the height here is f of xk. So that is the area of the one little strip. Then total area can be approximated, right, using summation. So if you summing up the areas of all the strips, and assuming you have n number of them, right, then you get an approximated area underneath the function f of x. Then of course, if you increase the strips from a number to an infinite number, then the summation sign becomes integral sign, delta becomes differential. So then you get the regular integral a to b and f of x and dx. Right? So that's the idea of how you derive the area underneath the function f of x. So now I'm going to look at the double integral using a very similar approach at here. So let's see. Here, okay. So let's see. I have a function z equal to f of xy. Okay, so given z equal to f of xy. And also a region R in XY plane. Okay. So here's the region R in the XY plane. Just arbitrarily draw the region R here. So when you integrate a single function, you have a region A to B, right? So now we're dealing with function two variables. We actually have a region, it's an area represented by a certain area. All right, so basically, if you pick a point in the region, then you will be able to find a value, right, on the surface, z equal to f of xy. Okay. So here's a question. So what is the volume? Okay, what is the volume below z equal to f of xy? And above region R. Okay. So let's say in your head, so I'm gonna not be able to solve that, but we'll just lay down here. So let's say you create, right? You going along the edge of R. Right? You're going along the edge R. You can create probably, I don't know, certain edges, right? So okay, on the top of the surface, and you have a traced out, okay, a part of the, it's like a walk, right? You put it right on the top, and then you try to measure the volume. So basically, what is the volume between the region R and the top surface? Okay. So we'll look at this. Essentially, we can use a similar approach to give us a double integral to give us this volume concept. So let's look at that in the next lecture, okay? How this double integral formula is properly derived. By the way, we'll have put up an announcement. We'll have our quiz numbers 3, I believe, okay, and next Thursday and next Friday, Saturday, just same format. Okay, the question will be on the multivariable function, partial derivative, and total differentials. Okay, so if you got any questions, feel free to come over. Otherwise, have a good weekend.